So we're going to be talking about the structure of an atom. And I'm smiling because I was thinking, now what do I have? How can you really show what an atom looks like? A lot of this stuff you've already had, okay? So just kind of bear with me. It's hard to kind of picture an atom sometimes, but it makes me smile just the same. So an atom is basically the smallest entity of a substance that you can't break it any further without screwing up its physical properties. So an atom is the smallest unit of an element that retains the chemical properties of that element. Thou shalt not smash any atoms in this class. Oh, lots to write in there. Okay. So related to an atom, then we have the word element. So we said, remember that little, that tree of matter? Matter can either be a pure substance or a mixture. And if it's a pure substance, it'll either be an element or a compound. So if somebody says I have a chunk of matter and it's an element, then all of the atoms are the same. They are all the same. So an element can't be broken down into any other stuff of matter by ordinary means. So when I say ordinary means, excuse me, the opposite of ordinary is extraordinary. So extraordinary would be the whole smashing the atom sort of thing. Nuclear, I get my fission and fusions mixed up. So that'd be nuclear fission, right? To split an atom. That would be extraordinary means. So some pictures of copper, kind of zooming in. But atoms are so tiny, 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 tiny. Okay, again, copper zooming in. I'm going to go ahead and see if this movie will play for us. Oh, that's a good sign. Something like copper. That's actually one that you need to know if you don't already know it. Okay. If we have something like copper that has 2 letters for its symbol, the first letter is capitalized, the second letter is not capitalized. Okay. A good example is cobalt. So, for instance, cobalt has 2 letters, capital C, lowercase o. If instead of a lowercase o, if you were to put an uppercase O, of course, now we're talking about the compound carbon monoxide. Yeah. So case does matter. All right, so which ones do you need to commit to memory? What do you need to recognize, either recognize or be able to give me the symbol of the element with the name of the element? And here they are by atomic number. We'll talk more about what atomic number is coming up. But atomic number is the number of protons. That's the number of protons in the nucleus of an atom. And I usually call the atomic number, that is the whole number. It's the whole number in the box for that element on the periodic table. So, for instance, you can even see it from here. See, Li is the element lithium, okay, and it's got the number 3 there. So 3 is the atomic number. Let's jump down to, let's pick something over here. Br, that's the element bromine, right? And its number, the whole number is 35. So that's its atomic number. So that's the number of protons in the center of a bromine atom. Okay, so we'll be talking about that. But now, if you want to, what I've seen some students do is to take their, is it the back that has a periodic table? Yeah. Take some periodic table and go ahead and find those. Sorry. Find those, and so make sure that you know the symbol with the name. Okay, so like what's the symbol for mercury? I picked a hard one. What's the symbol for oxygen? Oh, what's the symbol for aluminum? Al. It is Al. Very good. The symbol for mercury is Hg. See, that's a weird one. Yeah, so that's what's the symbol for sodium? Na. Yeah, exactly. So some of these just rattle off your, tip of your tongue. Okay, so there's just a handful, 7 actually, of the elements that under normal conditions you find on Earth, under normal temperature and pressure conditions on Earth, they buddy up. There's 7 of them. They're called diatomic elements. And you're going to want to know those too.
I'm sorry, can you re-say that? What was that?
Sure. They buddy up. Just it has to do with the way the electrons are. They never float around by themselves. So basically, hydrogen is the first one. So hydrogen is one of the 7 diatomic elements. So it buddies up. So you'll see a hydrogen. This is a chemical bond, another hydrogen. That's the way hydrogen runs around. We actually call that an H2 molecule. Okay? So hydrogen, just gaseous hydrogen, is H2. More importantly than hydrogen, let's pick on nitrogen. You guys would tell me the symbol for nitrogen is N, right? So here's one nitrogen atom, and here's another nitrogen atom. Okay, they run around as a molecule just normally. You won't see a single nitrogen atom by itself. It'll be paired up.
So all the others you can look for and find just a single one, but these
Right, exactly.
will always be paired?
They will be paired.
Okay.
And this bond right here actually is a chemical bond that I've drawn between these. It's a covalent chemical bond where, as you guys may have run into 2 types of chemical bonds, electrons are shared there. They're just, yeah. So like when we say, for instance, I think earlier we talked about chemical reactions in here maybe, where new substances are formed. You can take water, H2O, and you can add electricity. It's like electrolysis of water. Okay, and you can break it up. But I tell you, on the product side, on the right-hand side, you're going to see H2, and actually oxygen is another diatomic element. Let me go ahead and stick in a G here, and a G here for gas, and I'll put an L for liquid here. So hydrogen, diatomic element. Oxygen, diatomic element. Nitrogen, diatomic element. There's 3 of the 4. Yep. Oh, that's not balanced, shall we? Okay, let's go ahead and put a 2 there, conservation of matter, and put a 2 there. Does that make everybody feel a little better? I feel better. Okay. So the 7 diatomic elements, I have a few slides about the 7 diatomic elements. Okay, first, these are all listed in atomic, these are all listed by weight. Atomic number, increasing number of protons in them. Also, increasing how much they weigh. So notice a little subscript 2 means that actually they are a molecule running around. But, I say under under Earth conditions of temperature and pressure, the bet's off when you monkey with the pressure and the temperature as to what they normally be. So the way I learned this actually is this way though. The 7 diatomic elements, just rearranged a little bit. I don't know if you can kind of see the blue, but the blue actually spells out kind of like the German sounding name Hoffernickel. I don't know. So you could, the way I always remember that there are 7 of them is hydrogen is diatomic, oxygen diatomic, fluorine diatomic, bromine diatomic, nitrogen, iodine, and chlorine. So, long time ago, I learned it that way, Hoffernickel. But actually, they're not too bad to kind of remember because they are kind of near each other on the periodic table a little bit. So I'm going to reveal where they are. So hydrogen, diatomic, nitrogen, oxygen, and then you get to, some of you guys already know, this group over here, we're going to talk about groups like this. Yeah, halogens, exactly. This group right here are the halogens. And they have a lot of diatomic elements. So fluorine, chlorine, bromine, iodine. So there's not a whole lot in chemistry that I memorize. A lot of times it's just kind of, I don't think I memorize anyway. So Dalton's theory of the atom, Dalton's atomic theory. Now, there are some things on this slide in blue, and if you see it, I don't know if anybody's colorblind in here. Let me know outside of class if you're colorblind. That might make a difference in the class. But the blue means that that was part of his original theory that isn't quite right. So I went ahead and included it. So it was actually, I looked it up just before I'm going to go to this, hopefully. No, I'm not, because I don't have internet. But I looked it up just before class, and actually the person back, the Greek philosopher who first came up with the idea of an atom was like, started with letter D, Democritus or something. Okay. So in 1802, he came up with this atomic theory. He said all matter is made up of atoms, which is awesome. Then he said the atoms are indivisible and indestructible, and that's not true. They are under ordinary chemical processes. Okay. So then he went on to say that atoms of the same element are identical in chemical properties and mass. And notice the and mass is blue. One of the things we need to talk about with regard to the elements, you might be already familiar with this, is that an element, given element, can have multiple isotopic forms. So isotopes of the same element, they have different masses, but they have the same chemical properties. But Dalton was right when he said atoms of different elements will have different masses and different chemical properties. So that was right. And then Dalton went on to say compounds are formed by the combination of two or more atoms of different elements in the ratio of small whole numbers. And the word small is highlighted here. Actually, if you've dabbled in biology and looked at the size of DNA, RNA strands, you know that these are very large molecules. So it doesn't have to be small numbers. They can get very large. And then the last one, actually here in red, it was added to his original theory. So this is added, the red part makes it correct. So it's correct to say atoms are neither created nor destroyed. To me, this bullet down here is very similar to the first bullet on this slide. But it's correct to say that the atoms won't be created or destroyed during ordinary chemical processes or reactions. That's true. Okay. So there in our universe is a conservation of a lot of different things. We focus on just conservation of matter. Okay. So atoms are neither created nor destroyed during ordinary physical and chemical processes. Okay, since all matter is made up of atoms, we could also say that matter also is not created or destroyed. As long as you're talking about everyday, ordinary physical and chemical processes. Since matter is what has mass, then mass also cannot be created nor destroyed. So, conservation of matter. In our universe, the biggies, I guess, would be conservation of matter and conservation of energy. All right, so sometimes in the chemistry lab, we count on the fact that you can track matter. Matter is not created or destroyed. In fact, not this week's lab, but next week's lab, you're going to definitely count on the fact that the matter that you lose in your experiment, or excuse me, the matter that you gain in your experiment actually came in the form of oxygen combining with your magnesium. So, but just to kind of show you that, we've got two solutions kind of from left to right on the balance, reading 104.50 grams. We have silver nitrate and potassium chromate. And if we go ahead and mix them together, put them back on the balance, conservation of mass says that they should read the same mass, and it does. 104.50 grams. So notice though, and we'll be talking more about this, this sort of reaction is a chemical exchange reaction in which the silver ends up going with the chromate and the nitrate ends up going with the potassium. So over here you have silver chromate and potassium nitrate. It's what we call an exchange reaction. But it's got the same mass to end with. Okay? Okay. The law of multiple proportions, and I have an example coming up on the next slide, carbon monoxide and carbon dioxide. Basically, in this case, you have oxygen combining with carbon first as one and then as two, carbon dioxide. And so what this says, if two elements form more than one single compound like that, the masses of one element, which would be oxygen, combined with a fixed mass of carbon, is going to actually, you can leap in whole number ratios. So I'll kind of show you what I mean. Okay, there's carbon monoxide, CO. There's carbon dioxide, CO2. Okay, so if we just hold the amount of carbon the same, okay, then if you read this slide, what it's telling you is that from carbon dioxide to carbon monoxide, we have a ratio of 2 to 1 oxygens combined with the same mass of carbon. Okay? The law of multiple proportions. All right. I got to keep looking at my watch instead of that clock, right? Okay, so this is where all throughout this class, sometimes you're like, oh yeah, I've seen that before. So the three subatomic particles we need to talk about are protons, neutrons, and electrons. Okay, in physics, you'll talk about littler pieces than that. So I brought some BBs here today to kind of show you, represent a nucleus here in a minute. But kind of the way the solid thing in the center is the nucleus, kind of look like the nucleus of a cell. Okay? Okay. And then that fuzzy part is actually where the electron is going to be. It's kind of like the electron cloud. So yeah, I thought it was a slide. So this kind of tries to put in proportion the physical size of the nucleus, okay, versus the electron. We're going to call that electron cloud. Okay. One of the things about electron cloud is the electrons are hanging out there, but you never really know exactly where they are and how much energy they have at any given time. It's called an outcome of Heisenberg's uncertainty principle. So this could be the nucleus, right? So what we're going to find here in a minute is this is going to house our protons and our neutrons. It's coming up on the slide. Okay. But the electron cloud, what this says is, so if you make the nucleus the size of a BB, okay, then you need, think of a building 10 stories high. Put that BB halfway, so about 5 stories up, so you have 5 stories below and 5 stories, okay? And then to size, then the outside of the top and the bottom of the building is where your closest electrons are. So that's kind of how it goes. I can't remember which scientist it was, but actually the thing that stops us from falling through the floor, the thing that stops us from matter passing through matter, okay, is actually the electrons, the repulsion of the electrons between different atoms. Because honestly, most of an atom is empty space. But the electron cloud of one atom and the electron cloud of another atom, okay, it's that electron repulsion. I've heard it described, we actually, as we walk, are hovering over matter. Okay, atoms, our atoms, electrons versus the electrons of the atoms in the floor. So anyway, protons. What about protons do you need to know? Well, you need to know they're positively charged. A lot of times we'll take a proton and make a letter P with a superscript plus. It kind of emphasizes that. They are found in the nucleus of an atom, protons. Protons, it's like, how does this go? Like repels like, and unlike attracts. So the protons help keep that those electrons in electron cloud in check. Okay. Protons, I'm going to go ahead and write on this slide, have a mass of about 1 AMU. So protons, it doesn't sound like much, but it is. Protons have a mass of about 1 AMU. AMU is, it's like a mass, atomic mass unit. I usually call it AMUs like that, but actually the more modern way is just to call it U for AMUs. Okay, so, right, keep that in mind. Now, protons are important. I already kind of told you a few slides ago that atomic number is the number of protons. Atomic number is the number of protons. The number of protons in the nucleus of an atom says what element it is. So, like we were picking on bromine a minute ago, a lot of my passwords are like, come from the elements of the periodic table, but we pick on bromine, it's atomic number 35, so it has 35 protons in its nucleus. If I were to ask you what element has 19 protons in its nucleus, you would zip along and you would find, what element would you find? Potassium, yeah. So if you know the number of protons in the nucleus of an atom, you know what the element is. So, neutrons are important too. We use a little superscript 0 to indicate that they're neutral. They're like Switzerland. So neutrons are found in the nucleus with protons. So I said like repels like. So if you picture, I think this is what we call binding force. Okay? But if you picture that nucleus, and you picture all the little protons stuck in there, you picture those protons don't want to be with other protons. Okay? So the neutrons in there help kind of dilute that effect. And protons also weigh about 1 AMU. I have a little table coming up. Protons' mass, I should say, their mass, not their weight. Okay, but the mass of a proton is approximately 1. I'll go ahead and use the symbol U for AMU because that's what we should be using. Okay. All right. The last subatomic particle, the electron. Electrons are negatively charged, so the symbol for electron would be an E with a little superscript negative. Now that clock's kind of going in and out. It's like, it's on its last legs. Electrons are found in a cloud outside the nucleus. So we'll talk more about that cloud coming up, but in the class. So electrons are out there. And so like I said, I tried to kind of with the whole BB and the whole 5 stories and 5 stories. I mean, there's a lot of empty space for that electron to be. So with that in mind, when we talk about the size of an atom, when we're going to do that at some point in here, how big is an atom? Well, it's mostly empty space, but it's kind of defined by the volume that its electron is occupying. Electron or electrons. But here's one for you, and it's not much of a stretch. When it comes time for atoms to join together to make a molecule, so for instance, if we pick on water, okay, water has a central oxygen atom, a chemical bond hydrogen, a chemical bond hydrogen. Okay, there's a H2O molecule. So when it comes time for the hydrogen and the oxygens to get together, either here or here, it's all about the electrons that make that happen. Sharing, or in this case, or transfer of electrons that make those chemical bonds. So if that's what's making those chemical bonds, I guess to go specifically down to this, it says, in ordinary chemical reactions, those chemical bonds need to be broken and reformed so new substances can be made. All right. This always reminds me of like Christmas, like the whole red and green thing going on. So that's the nucleus. And then the dot, 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 dot kind of makes me want to itch. So that actually is representing the electron cloud. So electrons don't orbit like planets orbit the sun. Okay, electrons don't orbit the nucleus. But they actually exist in discrete energy levels in regions we call clouds. So this one, no, I don't think I'm going to play that because the last one didn't play. You ever heard one definition of insanity is to keep trying the same thing and get the same, expect a different outcome. Okay, so this is the table I was talking about with the 3 subatomic particles we're concerned about: proton, neutron, and electron. So we won't deal much with charge, but you can see that the fundamental unit of charge is the coulomb, okay? And you can see that the proton and electron have the same magnitude of charge. They're just opposite in sign, which works out great. When we talk about a neutral atom, right, it's going to have the same number of electrons and protons as it does protons in its nucleus. So here is how much each particle weighs in grams. I was looking at this in my office, and I'm like, well, that looks like electron is significant compared to neutrons or protons, but they're off by a factor of 10 to the 4th. So that is quite a bit. Instead of talking about grams, which is this first mass column, actually we're going to talk about how much atoms weigh in AMUs. So here is an AMU scale for you. So again, if you hear me or see me lapse into AMUs being AMUs being AMUs instead of U, so just bear with me. I'm in transition. All right, so atomic number. I feel like we've already talked about this a little bit. Atomic number is the number of protons in an atom of a given type of element. Okay, and the atomic number, for whatever reason, I should look this up one of these days, but we use the variable Z. So in chemistry, anybody talks about their Z, okay, they're talking about the number of protons in the nucleus of an atom. They're talking about the atomic number. And I talked a minute ago about if you have a neutral atom. So again, the magnitude of the charge on positively charged protons and negatively charged electrons, the magnitude is the same, they're just opposite in sign. So for every proton you have, as long as you have an equal electron out here, then it's a neutral atom. All right, mass number. So the mass number focuses on the nucleus. And if we were to revisit what is in the nucleus, in the center of an atom, it's protons and neutrons. So mass number looks at the nucleus and literally counts those particles. So mass number counts protons, which is set in stone if you know what element it is. But I'm here to say that neutrons, Mother Nature kind of sprinkled different number of neutrons in the centers of the nuclei of some atoms. The symbol for mass number, which makes me crabby, is A. See, it seems like atomic number should be A, but atomic number is Z, and mass number is A. Grr. So just to kind of emphasize, mass number is you look in the nucleus of an atom and you count protons and neutrons. Okay, so mass number, it's a little addition, number of protons plus number of neutrons. I can do that. So if we were looking at this, and of course we have electron cloud out here, okay, what element is that? 2 protons. It is helium. Very good. This is helium. Perfect. You know it's helium because it's got number of protons is equal to 2. All right. What's its mass number? I think this is a fictitious. Yes, it is 5. Very good. Sarah got 5 by taking the number of protons, which is 2, plus the number of neutrons, which I've drawn, is 5. That's just how that goes. I don't think helium has an isotopic form like that, but we just made one. So atomic number, the symbol for atomic number is Z, right? Okay, is unique for a given element. All atoms of the same element will have the same atomic number, same number of protons. Atoms of different elements will have different atomic numbers. Different elements, different number of protons. I'll buy that. All right. Mass number, symbol A, right, is not unique. In other words, atoms of the same element can have different mass numbers, but if you can't vary the protons, you're going to have to vary the neutrons, right? Atoms of different elements, now this blows my mind, atoms of different elements can have the same mass number. So basically you have an overlap of elements because of the number of neutrons in their nuclei. All right, so that's leading us to this ever important topic of isotopes. Isotopes, okay, by definition are atoms of the same element. But isotopes are different from each other because they have different masses. And so like I was saying, if you can't vary the protons, then you're going to have to vary the neutrons. So isotopes are atoms with the same number of protons, because they're the same element, but they have different number of neutrons. Put another way, it's like, I need to put it another way. Put another way, isotopes, okay, because they're the same element, isotopes are a pair of atoms or more that have the same atomic number, because that's the number of protons, but they have different mass numbers. The same Z, but different A's. While I'm thinking of it, Friday is the picnic out here, so don't forget to try to partake in that. It's from 11 to 1. So free food, free t-shirts, free get to see clubs and stuff, so should be good. Okay, so this almost, are you familiar with the oxymoronic term? It's just like it doesn't make sense term. So there's only one isotopic form of these elements. See, to me, isotopes means that there are, you can have a couple of different forms, the same atom with different mass numbers, okay, same elements, different mass numbers. But these you're only going to find Mother Nature only has a certain set of neutrons in the nuclei of these. These happen to have 2 isotopic forms that naturally occur. Okay, hydrogen. Have you ever heard of deuterium? Deuterium is heavy hydrogen. Helium has 2 naturally occurring isotopic forms. I bet neither one of them has a mass number of 5. Lithium, boron, carbon, nitrogen, chlorine, copper, and bromine. These have 3 or more isotopic forms. So 3 or more isotopic forms. Oxygen, neon, magnesium, silicon, argon, potassium, calcium, titanium, chromium, iron, nickel, zinc, and krypton. We named our latest batch of kittens, we call them the noble gases. So there's neon, krypton, and argon. Okay, so it's possible that you might want to indicate which mass number your isotopic form is. And so these are all carbon-12. Have you ever heard of carbon-14 dating? Okay, that means basically using the fact that life, as life is living, it incorporates a certain amount of your carbon atoms are going to be rare. They're going to be carbon with a mass number of 14. And then when you die, then that starts to decay. So basically they look at how much is left to know how long ago it was that you were alive. So these are all ways to show carbon-12. Carbon with a mass number of 12. Notice my favorite one, and actually we're going to be some of your homework coming up is going to be using this sort of convention of showing an isotope of carbon. So the symbol for carbon is C, right? This is the mass number 12, which is the number of protons plus neutrons, right? And the 6 is kind of redundant. It's like any good periodic table, you see the number, the atomic number for carbon is 6. Okay? But the thing that's unique to that isotope is the 12, the mass number. All right. So like you saw on the previous slide, all we need to do is to give the mass number and the element, I guess. All right, so here we go. There is no element X. There's an element XE, xenon, but there is no element X. Only in like Powder Puff Girls, I think that the professor made a...
Chemical X.
Yes, thank you, chemical X. So, kind of the shorthand notation, like the one I circled with carbon 12 and 6, superscript 12 and 6, that's kind of a good convention to go with, where the top number is the mass number A, and the bottom number is the atomic number Z. All right. So, kind of if you're a visual person, here we have boron. It has, both of these boron atoms have 5 protons in their center, but the left one has 5 neutrons. That makes 5 plus 5, so a mass number of 10. Then the right one has 6 neutrons. 5 plus 6 is 11, so its mass number is 11. So let's do a little game, shall we? So this is shorthand notation. Okay, we're dealing with fluorine here. And we should be able to answer these questions. Let's see, you might need 2 hands with this, but how many protons does it have? How many protons? Oh yeah, I'm liking it. If it's neutral and it has this many protons, how many electrons does it have? The same, very good, 9 and 9. Well, how many neutrons does it have? 10. Perfect. They're kind of fun. You got it. 9 protons, 9 electrons if it's neutral. And by the way, and we have an example coming up here in a minute, but you know it's neutral because there is no charge up here in the upper right-hand corner. Okay, that's where the charge would be if it's not neutral. I'll put charge, question mark. There's nothing up there. So let's do another one. Before we do another one, which actually you're going to see a charge up there, let's talk about ions. This is our first look at ions. We'll be talking more about ions. But if we just limit ourselves to ions that have only one atom, monoatomic atoms. Monoatomic ions, excuse me, monoatomic ions. They form because an atom has either lost, okay, here, check this out. If an atom loses electrons, does this make sense? It will become positively charged. If it loses electrons, it will become positively charged. Okay? And if it gains electrons, it will become negatively charged. And I want to kind of emphasize what little bit we've been talking about this afternoon. You know, picture your nucleus and your protons are in there and your neutrons, but protons aren't going anywhere. So the only thing that's going to happen is electrons are either going to come and go. Okay? If they go, it's going to be positively charged. Basically, your protons are going to take over. If you dump on electrons, you're going to have more electrons than you have protons, so it's going to be negatively charged. Okay. So since an ion, by definition, is charged, okay, that means that the number of electrons in the cloud are no longer equal to the number of protons in the nucleus. So we call a positively charged ion a cation. It becomes positively charged because it lost electrons. Electrons. And sometimes I hear people call this a cation. It kind of looks like cation. Cation, cation. And then I hear people call this an anion. And I almost see the word anion in there. Kind of. But an anion is a negatively charged ion. So it's negatively charged because it gained electrons. So then if we're writing, if we're dealing with something, an ion, we still use the symbol for the neutral atom, okay? We still put the mass number and the atomic number, A and Z. But now, like I said, we have to put something charged up here in the upper right-hand corner. If it's positively charged, we'll put plus, blah, blah, blah. If it's negatively charged, we'll put minus, blah, blah, blah. Or blah, 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 minus. For a cation and an anion. All right. So let's do one of those. And we're going to answer the same questions. How many protons? Well, you saw 20. There's 20 protons. Does that make sense? Because it's still that number in the bottom left-hand corner. That's the atomic number. But now, is it electrons next? Mm-hmm. Electrons are a little different. First off, are we going to add electrons, take 2 away? We're going to take 2 electrons away, exactly. So 20 minus 2 is 18. Perfect. There's 18 electrons. You all good with that? It lost 2 electrons. So now in the center of that, in the center of this particular ion, the nucleus has 20 protons. Okay, we know it's running around with a +2 charge. Okay, so it's got 18 electrons here. Okay, so basically it's got an excess 2 protons. Okay, so how many neutrons does it have? 19. Perfect. And I can tell you on your Unit 1 exam, you're going to have a couple problems like this. Or a problem Let's do an anion. So how many protons? 17. I'm liking it. How many are there more electrons or less electrons? There's one extra electron, 18. I'm liking that. Very good. And then how many neutrons? 19. Sometimes I use my calculator for these. 19 neutrons. Very good. Any questions? So we did make it to the assignment slide, and I got 250 right here. Now, I do have some hints here. I must already apologize for the bad hint I gave you the other day. 2 of you at least showed this to me. The volume of a sphere, and you're fine for the homework handed in. You're totally fine. But I said the volume of a sphere was 3/4 pi r cubed. No. The volume of a sphere is 4/3 pi r cubed. I probably won't get that one wrong for a while. If you went ahead and used this in your homework, you're fine. You're totally fine. It's fine and strong here. So these look like this. I won't belabor it as much as usual. Which one is it? What's it start with?
223.
Oh, good, thanks. Okay, so this is what it looks like. They're kind of fun. You guys sound like you were just definitely tracking along. You already see 23. It gives the shorthand notation where you have the mass number, or no, you're supposed to write it in shorthand notation. So you have to look up information for cobalt. You need its atomic number to finish that thought. For number 24, I went ahead and gave you a hint you might find helpful. For 24, it says, what is the percentage of fundamental particles in the nucleus that are neutrons? I just would kind of diagram it down here. They tell you it's mercury, Hg, with a mass number of 202. You automatically can go ahead and knock out protons and neutrons from that. And then, of course, percent neutrons is the ratio of neutrons to neutrons plus protons times 100%. This one, it's kind of fun. You should have fun with it. Fill in those little dashes. I know. Notice, though, in the instructions, by the way, the answers are in the back of the book, I guess, or because it's 25 and it's red. So you should be able to look this up. But some of you can't fill in the blanks because you don't have enough information. It's kind of fun. Playing detective. Okay, this one, my suggestion was for each one of these, I would knock out electrons and neutrons, because then it asks you to put them in order of increasing. Electrons, neutrons, and mass. That's what I would do. For 33, actually 33 and 34 go together hand in hand. You have the answers to 33, but 34 you're on your own. But I would, for each of these, how many are there? There's not many, 7. For each of the 7, I would knock out the 3 subatomic particles and go ahead and answer it that way, because they ask you an assortment of questions. I just think it would be easier, you know, less mind-bending. Okay, but it's kind of like, it reminds me of Clue, where you have to figure out who's who. Okay? All right, so we'll see you on the flip side. See you tomorrow.
So we do Friday.